So we talked about a couple different notions of centrality, and one more is degree centrality, which is just the degree of a vertex divided by the total number of edges, right? So this is the fraction of all the edges that touch me. Okay. And so maybe this is a good candidate for our, we're seeking some notion of importance of a vertex in a graph. All right. So imagine we have a social network, and then the degree of a vertex is the number of friends you might have. Well, people with more friends are in some sense more important than people with fewer friends in the context of a social network. Fine. But if, say we both have 5 friends, well, then we have the same degree centrality by this definition. But what if your 5 friends are they themselves much more connected than my 5 friends? In some sense, you should be more important than I am in the context of this social network. And this notion of degree centrality doesn't capture that. All right. So let's see if we can improve on this. Well, another notion of centrality is eigenvector centrality, which is actually just PageRank. And so if you are familiar with PageRank, or this may be another way of looking at it, and if you're not familiar with PageRank, then this is a great way to develop an intuition for it. So the basic idea for computing PageRank is, while things are not converged, for each vertex in the graph, compute the rank of that vertex by adding up the ranks of all of its neighbor vertices. Okay. All the incoming edges, if we assume a directed graph. Right? So this allows you to say, well, look, if the President of the United States is connected to you by 1 hop, is your friend, say follows you on Twitter or something like that, well, then you're more important than somebody who doesn't have such an influential person in the graph. You add up the rank of the president to your rank. Okay. Meanwhile, you distribute your rank to all your friends, right? So, and you do that. You repeat this passing of rank, of weight, of importance across the network, across the graph, until you reach some convergence condition. And then that convergence condition gives you a relative score of who's more important than who, perhaps. Which vertex is more important than which other vertex. But there's a couple of problems with this approach. So one is, one page or one person in the social network with millions of outgoing links, if they link to me, that's somehow less valuable than a page that only links to a few people, right? So if you've got one of these crawlers that follows everyone in order to collect as much, follows everyone on Twitter in order to collect as much data as possible, it's not very important that they follow you, right? You don't consider that to be very prestigious that you have some automatic robot crawler following you. Meanwhile, if you have an aggregator page that sort of links out to everyone on the internet, similarly, that's not very important that it links to you. So somehow you want to make sure that they divide their rank amongst all their outgoing edges, as opposed to just give their total rank to each outgoing edge. Fine. So that's easy to fix. Another notion here is that, well, if I'm 27 hops away from Barack Obama, that's less important than if I'm 1 hop away. And so we really shouldn't count that as very influential. And so we need some sort of a damping factor that as you get further away, it sort of lowers the importance. Okay. So you combine these two notions together and you get the definition of PageRank as it was published. And there's a couple of variations on this, but this is the one to know. Okay, so while not converged, the rank of vertex A is the sum of all the ranks of the vertices that link to A, but each one is divided by the total number of outgoing edges. So in this notation, we assume that there are edges B linking to A, C linking to A, D linking to A, and PR of A, the page rank of a vertex X, is going to be the page rank of the vertex X. L of X is the number of outgoing links from X. And so for the page, we take the page rank of B and divide by the number of outgoing links away from B. Take the page rank of C, divide by the number of outgoing links away from C, and so on. Add all that up, and that's all the contribution to A. And then we multiply by a damping factor to make sure that what we pass on diminishes over time as we get further and further away. And then this other term in this expression is just to ensure that all the ranks sum up to 1, so that we can sort of interpret them as probabilities. And in fact, you can directly interpret this as a probability, which is another way of looking at PageRank and deriving PageRank, is to take random walks around the internet, around the graph, right? So you start on a random vertex and just start walking make a choice at random among the edges, the outgoing edges, and just traverse around. Well, if you do this a bunch of times, you can derive how likely it is that you'll spend time on some particular vertex versus some other particular vertex, and that will exactly be the PageRank. And so this is sort of, all roads lead back to Wikipedia or CNN or some other very, important vertex in the web graph. So that's PageRank, and what I wanted to point out before we move on is just the relative simplicity of this, right? It really comes out of an intuitive notion of trying to figure out how can we measure the importance of a vertex in the graph. And so, you start from very simple notions of, well, maybe important means just the one with the highest number of edges that link to it. Well, there's some problems with that, so let's see if we can fix it. Maybe it's the one with the most number of paths that go through it. And maybe we don't care about all paths, we care about shortest paths. So that gives you another notion of importance. And then you say, well, that's got some problems too. What are the properties we really want here? Well, maybe it kind of captures, the importance of your friends needs to be added in there somehow. And you can sort of walk through this and come up with where PageRank came from. So the way it's presented, just like a lot of these things, are presented in terms of a finished formula, and then you kind of have to work out back, reverse engineer where it came from. But a lot of these things are developed very intuitively, and the formula is only used as a notion to express the intuition in a precise way.